girls, get down. Get up.
Alrighty, so what is an initial value problem? What do they give us differently than if we were just given a regular ODE? So what an initial value problem, IVP, gives us is, so this gives us an ODE, and an initial condition. That's what it's called, initial condition. Okay, so these two parts are very crucial. So the ODE by itself, this allows us to find the general solution. So this allows us to find, like I said, the general solution here. Okay, and that means like our plus C or times C or anything like that. So let me write plus C or times a constant or anything like that. Something to do with a constant, and we have a general solution set. Okay, and this initial condition part, this is like an initial condition, also known as initial value. This allows us to pin down the exact constant C that we're talking about in our general solution, in order to get the unique solution. Okay? Okay, so these are basically just an overview of initial value problem, right? So we're given an ODE and initial condition. We work with the ODE first, just to find that general solution. We just accept there's a plus C or a times C or something like that, some constant involved. And then we look back at our initial condition that is also given an initial value problem. And we're going to pin down that exact constant C, and we form our unique solution. So let's do an example of this on the next slide. So let's say we're given y of t is equal to -1 over t minus c. Let's say that this thing is a general solution. So this part, this problem has already been kind of halfway done for us. To the ODE, which is given by y prime, is equal to y squared. Okay, and then what we're going to do now, here's the problem part. So they already did the first half. They found the general solution for us, because we don't know how to find those just yet, okay? So they found the general solution, and then what they're going to ask us to do is find the particular solution satisfying the initial condition of y of 0 is equal to 1, okay? So in this case, what does this mean? So we have our general solution here, okay, that contains some kind of constant in it that can vary, right? And then, and this is our ODE, okay? So this is our ODE. So what we're going to do with this now is take into consideration this thing here. This is our initial condition, okay? This basically just tells us that when t is equal to 0, so when t is equal to 0, our y, the value of our single variable function, is equal to 1. Okay, so when we plug this in, so we can kind of just solve for it using our general solution. So that means y of 0, so we're going to plug in a 0 wherever we see a t, so this will be 0 minus c, is equal to, so this thing we know has to equal a 1, right? Y has to equal 1. So this is overall a 1, and here we're just going to use that and solve for c. So we have -1 over -c, and then is equal to 1. So that means that we have 1 over c, positive 1 over positive c is equal to 1. And when we switch those around, we just take the reciprocal, so c is equal to a 1. All right? And now that we've pinned down this specific constant c, now we can just plug it in, right, into our general solution and make it automatically a particular solution. So our particular solution is going to be y of t is equal to -1 over t minus, instead of c, now we know that c is equal to 1, so we just plug in a 1 right there, and this is our particular solution, okay? Particular solution, and we have found it. Okay, so here's another important topic that we should discuss. It's called interval of existence. So let me start out by defining it. So an interval of existence is basically the largest interval, as given by the interval thing, right? So largest interval over which, we're going to get all technical here, so over which the solution, or a solution, the solution can be defined, because we don't want anything that's undefined, right? Because it's undefined, and remain a solution. Remain a solution. So there are two important parts here. So what does this mean? So that means when we get some kind of solution, let's say our y of t, we find a solution, a general solution or a particular solution, let's say, and for some values of c or for anything like that, our solution will be undefined. Okay, so in doing so, we kind of define these intervals, and there could be multiple intervals as well, such that this solution here is defined. We want this to be defined, okay? And then the second part, so this is the defined part, and then we have remain a solution. So that means like when we have our original ODE, sometimes certain values of this whole entire function, let's say we have something like this, where we have y prime is equal to 1 over y or something like that, right? So for example, when our function here is equal to 0, though it is defined because it has a value of 0, it cannot satisfy this ODE because 1 over 0 is undefined itself. So in this case, y of t is not allowed to be 0 anyways. So we'll run into problems like this in the future. You don't have to worry about them too much right now. We'll address those as they come up. So in this case, though, we're going to do an example, okay? So let's say we have an example and we have like y prime is equal to y squared. This is the one we've done before. So then our y of t is equal to negative 1 over t minus 1. Remember, we solved for the particular solution here. Okay, and then our initial condition was y of 0 is equal to 1. That's what allowed us to solve for that constant c, which turned out to be 1. Anyways, so let's look at our solution here, our particular solution. So we see that, well, when t is equal to 0, or sorry, not, when t is equal to 1, a positive 1, that means that our denominator is equal to 0, which makes our y of t undefined, which is not good, right? So, but this is good in the sense that now we know, okay, so where is y of t undefined? So we can construct our intervals around that area, okay? So we don't want our t equal to 1. That's basically it. So our intervals for t can go from negative infinity up to 1, and then we have a rounded bracket here. That's important. We're not including 1 because we want our function to remain defined, right? And then this is in union with, that just means like it's also part of the solution set. 1, we're starting at 1, rounded bracket again, and going all the way up to positive infinity, okay? So these are the possible intervals here. And then what we do to pick one of these intervals, because we can't have both of them existing at the same time, really. But for our initial condition, we're going to look at this guy here. And remember, our t was equal to 0. That's what they told us. So t is equal to 0. So then we just look for the interval within which this t exists, basically. So where is 0? That would be in this bottom interval here, okay? In the one that includes negative numbers and all numbers smaller than 1. Then we would pick this as our interval of existence, okay? So ultimately, our interval of existence for this problem of existence is equal to, well, it is negative infinity up to 1, okay? So that would be our answer for the interval of existence for our initial value problem. Okay, now for the last topic of this concepts video, I'm gonna talk a little bit about what we're talking about, like geometrically, what all of these equations mean and everything. So let's say we have some like first order ordinary differential equation, right? Because we have the highest order here is the first derivative. So we have y prime is equal to some function of t and y. So let's say we have something pretty simple. So this is y prime is equal to y. This is just an example of an ODE, okay? So we're going to study this. And let's say, okay, so what does this look like graphically? So let's graph this. So we have t, y versus t, okay? Both of these are functions of t. So y prime of t is equal to y of t. So this means like, well, okay, so if we label this 1, 2, 3, then we have 1, 2, 3 down here, negative 1, negative 2, negative 3, then we go across on the t and to the left. Okay, so this means that our first derivative, which determines the slope of the tangent line, right? Remember that? So first derivative corresponds to the slope of the tangent line at any given point. Slope of tangent line Okay, so that means that, well, when y is equal to 0, when our y value is 0, so when we're on the t-axis, that means that our slope is 0. So I'm going to draw these little slope lines, okay? So something like this. So we have horizontal slope lines. And when y is equal to 1, so when we're up here on this line, moving the screen, when we're up here, that means that our slope is going to be a positive 1. So positive 1, positive 1, positive 1, positive 1, positive 1, positive 1, going across, okay? When we're at a height of 2, that means our slope is going to be 2. So it comes steeper and steeper, right? See that? So we have something like this, okay? And then keeps going up and up and up. So it becomes steeper and steeper as we go up. Now let's look below the t-axis, and we have negative 1. So when y has a value of negative 1, then our slope is negative 1 at each of these. So then we have negative 1, negative 1, negative 1. So pointing down like that. And then becomes steeper and steeper, but this time with a negative slope, okay? So everything is basically growing away from the t-axis as time goes along there. All right, so what's going on here? So this is like our general solution. That's what I just did here, okay? But if we were, per se, to have some kind of initial condition, such as this, where we had, like, I don't know, y of 1, let's say, y of 1 is equal to 1 or something like that, then we would give that would give us, okay, well, our t is equal to 1 and our y is equal to 1, so that must mean we're at 1, 1. We're right here, okay? So this is our initial condition. See that? That's our initial condition, which allows us to graph a specific graph in between all of these tangent lines. So this graph that I'm drawing, that would be our particular solution, okay? Alrighty, so right in there, let me draw it nicely. Okay, this would be our particular solution. Whereas before, if we didn't have that initial condition, these are basically all of the solution sets that are given by the general solution, okay? But when we do have that initial condition, it does narrow it down to just this one curve, okay? Alrighty then, that wraps up our concepts video on differential equations and their solutions. I hope that helps, and I'll talk to you in the practice problems video if you watch.
My dog, get up.